Hello, and let's get started on Chapter 2. Chapter 2 is about logical thinking. It's going to try to show you how to think logically about situations, how to take situations that you run into and put them into conditional statements, if not verbally, at least in your mind. If you were not in class, then I would encourage you to do this. Take notes as you go through this slideshow. You'll be able to pause it and take some notes. If you were in class, you've already taken those notes, and I'm looking through them for your thoroughness. Try to make them less confusing than this picture. So why is this picture confusing? Well, if you just look at one part of it, it maybe doesn't look so bad until you start to notice things like, well, what? This looks like maybe an inside corner here, and maybe it's an outside corner there. This looks like it's on the front of the picture, but as you trace it up, it's clearly on the back of the picture. So there's some weird things going on here. So we ended that last lesson by saying we can't go on like this. It revealed that we need a stronger foundation for our study of geometry than the informal approach that we have used so far. By informal, I mean we've just been using things that we haven't really proven as true. We don't really understand why they work. We're not satisfied with that. Euclid led the way to this understanding by organizing geometry into a deductive system with definitions. We've had some of those, recall them. Some assumptions that we call postulates. We have not had any of those yet. We'll be getting some soon. And then logical methods. That's what we're going to focus on in this chapter for proving our conclusions. And those conclusions we call theorems of geometry. We're going to be looking at some common theorems in this chapter. But before we can do that, we need to actually look into what are used to make theorems, conditional statements, in other words. And that'll help us determine the nature of deductive reasoning. So on page 42 in class, we'll have read through this, and then you can review for yourself and try to explain to yourself what is a conditional statement. So pause this a bit, think back to what we did in class. Can you answer that? Hopefully you paused and challenged yourself. So it's two clauses. They look like sentences. Sentence parts with the subject and verb. So the conditional statement has two clauses. One of them, and I'm not going to say the first one because we found out that the order can vary. One of them begins with an if or when idea. If this is true, or when this happens. The other clause begins with a then, or if it's not written in the sentence, at least the idea will be there. If this is true, then that is true. When you do this, then good things happen. There I had the word then in there. But some conditional statements you'll run into when the word then is not written. So some examples. This has happened to you. If you break your lead, that would be called the what? Yes, the hypothesis. So where's the hypothesis in this sentence? Well, you should be looking for either the idea of if or when. And there you see it. When you study correctly, then you are more prepared for your test. These are not strange, unusual sentences, are they? They're the types of sentences you use every day. Or at least you hear every day, probably. Where's the hypothesis here? Hopefully this worked out. I tried to pause it because I got a phone call. So we'll see if this video ends up smooth or whether you get all the message of my phone call there. So what we were doing is we were looking at sentences here and checking for the hypothesis, the if or when. Do you see it in this one? When you get more sleep, sure, that's the one. How about in this sentence? Find the hypothesis. Again, we're looking for if or when. Yes, so here's this. This is important to realize. You can't always assume it's going to be at the beginning of the sentence. This one you see is near the end. If you have more points than your opponent in volleyball. And this one also points out the fact you don't necessarily have the word then, but it's there. You win the game. Then you win the game. You'll notice these previous two didn't have the word then in them either. So now what we're doing is showing the conclusion of the conditional statement. Then you will not be able to write. Then you are more prepared. Here it doesn't have the word then, but it's there. If you lose some money, you will be poorer. Then you will be poorer. Then you are more fun to be around. Then you win the game. So conditional statement then, kind of summarizing. The hypothesis is the clause that begins with the word if. The conclusion is the clause that begins with the word then, or the idea. So in this particular one, that's the hypothesis. And then that would be the conclusion. I found a book on the rules of the game. It's a little old, as you'll see from the examples, but I've printed out some statements, some rules from that. I'd like you to look for the hypothesis in each one first. Do you see it there? That one's pretty easy. You can see that if an opponent touches the ball. Here's the second one. Where's the hypothesis? Right, there it is, if a team does not have at least 2 players. And sure, right at the beginning here, if a kicker breaks the law. Here we go. Now you see one near at the end again. These are still conditional statements. They still have a hypothesis. They still have a conclusion. Here you can see kind of an old rule. This was volleyball. A long time ago, back when I played. Now, then you, one more here. If he is within his opponent's half. Of course, then all the rest of these are the conclusion. It's the then idea. We don't always see and then. As a matter of fact, none of these have a then actually printed in them, but they are all the conclusion. All right, this next part was in the author's previous book, but they were eliminated in the new book, but I think they're very important. So we are going to learn about some other related conditionals. Sometimes we shorten it up. Instead of conditional statement, we say conditionals. These are important to know, so if you missed class, you need to write these down for yourself so you can help remember them. One of them is called the converse of the original statement. The converse. You have to find a way to remember what this is. So here's our original statement. We'll work with this for a while. If the plant is green, then it has chlorophyll. So you can see the hypothesis. If the plant is green, then the conclusion, then it has chlorophyll. The converse of the original statement interchanges the hypothesis and conclusion. It doesn't just write them in a different order. You don't say it has chlorophyll if the plant is green. That's not the converse. To interchange means to make the hypothesis the conclusion and the conclusion the hypothesis. Pause it and try to write that out. Or at least get it in your head. Okay, if you're back, is this what you ended up with for the converse? If the plant has chlorophyll, then it is green. So we interchange the hypothesis and conclusion. Converse. How are you going to remember that? It's always good to try to have a memory mnemonic. Mine is a little bit strange. Back when I played basketball, Converse shoes were all the thing. So I just picture putting my shoes on the wrong feet. So instead of the left on the right and the right on, left on the left and right on the right, I have interchanged them. I put my right on my left and my left on my right. So it's very random. Probably won't work for you, but it works for me. The converse, I interchange my shoes. Here's the second conditional. It's called the inverse. And in usually means like not. So if this again is our conditional statement, the inverse negates the hypothesis and conclusion. Negate Yeah, it's like negative, saying no or not. And that's usually what we're going to see here. We don't interchange them. We leave the hypothesis, the conclusion, but we negate them. Why don't you give that a try? Pause it and give it a try. So if you're back, does yours look like this? If the plant is not green, we negated the hypothesis, then it does not have chlorophyll. So that is the inverse, negating. I don't have a fun way to remember that one. Hopefully you can come up with one. This word you will not see anywhere but in geometry, probably, or maybe in some other logic class or a courtroom or something. Here's our original statement. The contrapositive does both of the things we have just covered. It interchanges and it negates. Give that one a try. Pause and try to write it out or get it in your head. How's it going to sound? Interchange and then negate. So here's what it should look like. If the plant does not have chlorophyll, then it is not green. Notice we took the conclusion and we said not have chlorophyll, and we made that the new hypothesis. We took the original hypothesis, then it is not green, and negated it. So that is the contrapositive, interchange and negate. So here we have a conditional statement, and the challenge is to go ahead and write out these three conditionals. This is our original. Pause this, give it a try, then come back and see if yours match. I'm assuming you paused and that you're back now. So the converse, remember, all we do is interchange, so it should look like this. If it is a pentagon, or if a polygon is a pentagon, then it has 5 sides. The inverse, remember, you negate. So don't interchange them, don't switch them, leave them, but negate. If a polygon does not have 5 sides, then it is not a pentagon. The contrapositive, you do both. If a polygon is not a pentagon, so interchanged and negated, then it does not have 5 sides. Sometimes these are all true, and sometimes they're not. Take a quick look. Is it true that if a polygon is a pentagon, then it has 5 sides? Yeah. How about, is it true that if a polygon does not have 5 sides, then it can't be a pentagon? Yeah. How about this one? If it's not a pentagon, then it does not have 5 sides. Yeah, that seems true too, doesn't it? So in this case, all 4 are equal. Is that always the case? Let's check out another one here. If a polygon is a rectangle, then it has 4 sides. Is that true? Sure, a rectangle has 4 sides. Go ahead, take a minute, pause this, and write out the conditionals for this original statement. As you do, pay attention to them and see if you think they're true or not. So you're back. Hopefully you went through the exercise. Here's what they would look like. If a polygon has 4 sides, then it is a rectangle. Okay, we interchanged. Here's the inverse. If a polygon is not a rectangle, same order, we just negated them, then it does not have 4 sides. And finally, do both, interchange and negate. If a polygon does not have 4 sides, then it is not a rectangle. So did you take a look at the truth of these? Are they all true? Is it true that if a polygon has 4 sides, then it is a rectangle? No, of course. You could have a rhombus, you could have a parallelogram, you could have a kite, several things. How about this? If a polygon is not a rectangle, then it does not have 4 sides. Well, no, that's not true, is it? If a polygon is not a rectangle, well, a rhombus is not a rectangle, but it sure does have 4 sides. So these two kind of mean the same thing, don't they? How about this? If a polygon does not have 4 sides, then it is not a rectangle. Is that true? Well, sure, it's got to have 4 sides to be a rectangle. So it looks like the contrapositive and the original statement are both true. They mean the same thing. And the converse and the inverse seem to suggest the same thing. So when you see a conditional statement, you got to be a little bit careful about what's true and what's not. So we'll try another one here. I've got the hypothesis in yellow, gold, and the conclusion in green. Pause, write them out, come back, see if we agree. And again, pay attention. Are the statements you're writing true or not? So here's the converse. If a shape's diagonals are equal, then it is a rectangle. Here's the inverse. If a shape is not a rectangle, then its diagonals are not equal. And the contrapositive, interchange and negate. If a shape's diagonals are not equal, then it is not a rectangle. I think I've got a picture here to show this one. You may not be ready for it, but if a shape is a rectangle, then its diagonals are equal. If a shape's diagonals are equal, then it is a rectangle. Well, here's what we call an isosceles trapezoid. And in this case, the diagonals are equal, but that certainly is not a rectangle. So here was a case where the original conditional statement and its converse, and the inverse, by the way, were not true. So we introduce something new here now. An Euler diagram is the way that's pronounced. Looks like Euler, but it's Euler, an Euler diagram. We use it in logic, and it helps us to picture how conditional statements relate to each other. In those, we use 2 circles, one inside of the other. Maybe you've seen something like this before in your math. The smaller circle represents the hypothesis, so that's that one. And the larger circle is the conclusion, up here. And if you remember, this could also be called the if part of the conditional statement, and this would be the then. So again, Euler diagrams. The small circle is the if, the large circle is the then. Okay, now what's the point of this? What's the deal? Well, if you think about it, if something is in this A circle, the hypothesis, it clearly has to be in the B circle, because every part of the A circle is inside of the B circle. But it is always true that if something is inside the B circle, then it has to be in the A circle? Well, if it were right here, sure. But it could also be here. It could be in the B circle and not be in the A circle. Which, by the way, maybe you caught on to that already. That would be the converse, wouldn't it? If we start out with if A, then B, the converse would be if B, then A. And you can see this picture would not work for that. You could be here in B and not be in A. Well, your book has I guess it's a crime scene investigation. And in that, I guess the hands on the watch were changed. So the detective, I can't remember if it's Hercule Poirot or whether it's Sherlock Holmes. I am actually turning and looking at my book. It's Poirot. So he determined this. He came up with this conditional statement. If the hands of the watch were altered, then the time must be important. And we can use an Euler diagram to demonstrate that. If that's true, the hypothesis, then that's true. So we're back over here now with a pentagon. If a polygon has 5 sides, then it is a pentagon. Oh, that's right. We're going to make an Euler diagram here. So let's see if I can get my pen. Why don't you give this a try? So if it's an Euler diagram, I'm going to have a large circle. That is not a very good circle, but this is with my mouse. So there's a smaller circle. So if a polygon has 5 sides, so You don't always have to write everything out when you do these, just so you get the important part. So of the hypothesis, 5 sides, and then the conclusion, then it is a pentagon. So for that statement, I would be content with this that you were writing, but I would hope your handwriting would be much better than this. Oh boy. Okay. So if a polygon has 5 sides, then it is a pentagon. That's how you would use an Euler diagram here. How about this one? Try to make one for yourself here again. Pause it and see if you agree. So you're back, and here is my conclusion circle. Here's my hypothesis. Don't know why it makes those lines. So if a polygon is a rectangle, so in here I would write rectangle, rectangle, and then I would say 4 sides. So this is how you use an Euler diagram. So now I'm trying to think about this. Okay, so if you've got a rectangle on your paper or in your hand, whatever, if it is a rectangle, it would be in this circle, and it would have to have 4 sides because every part of the rectangle circle is in the 4 sides circle. All right, let's go on. Here's another statement. If you go to a manual, then you are a lancer. So where am I going to put these? Well, where's the hypothesis? Go to a manual, so it goes in the small circle. Then you are a lancer. Do you agree that every person that goes to a manual has to be a lancer? Well, yeah, because that's what our mascot is. And in the Euler diagram, every part of this small circle is in that larger circle. So in other words, if you go to a manual, then you are definitely a lancer. Let's take another look at this, though. Here's that conditional statement. What's the contrapositive of that? Give you a second to think about that. Pause it to challenge yourself. The contrapositive, are you back? So if you are not a lancer, then you do not go to a manual. Interchanged, negated. Not lancer, then do not go to a manual. Let's draw an Euler diagram for that. If you are not a lancer, then you do not go to a manual. Can we use the same picture we started with? Does this work? Yeah. If you are not a lancer, where could you put a X here? No, that would be being a lancer, wouldn't it? So I need to erase that. That isn't right. Could I put an X here? No, because that doesn't fit. It says you're not a lancer, and every part of this circle is inside of this one. So I need to get rid of that. Get the pen back. The only place that you can say you are not a lancer where that would be out here. And it seems pretty clear that if you're out here, if you're not a lancer, there's no way you can be going to a manual. I think that makes logical sense. So something to note, that the same Euler diagram works for both the original conditional statement and its contrapositive, and you'll find that to be true every time. So here you see the first one. If you go to a manual, then you are a lancer. Here I've got the same diagram. If you are not a lancer, then you do not go to a manual. We say, we'll get this word in a bit, but we say that these two sentences are logically equivalent. They mean exactly the same thing. Not true, however, with the converse and the inverse. Let's take a look. Pause again. Challenge yourself. Did you get it? Converse. If you are a lancer, then you go to a manual. If you're thinking about this, you probably already see the problem with this. Depends on how many other high school mascots you know. Let's do our Euler diagram. Can we use the Euler diagram we used before, which looked like this? If you go to a manual, then you are a lancer. Will this work? If you are a lancer, well, I could put one right here. And yes, I'm a lancer, but I'm not at a manual, am I? Is that a possibility? Well, sure, Manitowoc Lutheran, they are the Lancers. Maybe you know some other high schools whose mascot is a Lancer. So we can't use this diagram. If we'd have chosen our X here first, yes, we are a Lancer, and yes, we go to Emmanuel. But the fact that there are two locations that satisfy the statement means that this Euler diagram will work, or will not work, I'm sorry. So you can see the Euler diagram doesn't work for the converse. But what if we take that converse statement and try to draw a diagram that works? So let's take this hypothesis. If you are a Lancer, put it there, then you go to Emmanuel, and we'll choose our X right here. If you are a Lancer, then you go to Emmanuel. Okay, back up 1 second. So we've got the converse. If you are a Lancer, then you go to Emmanuel. This diagram fits perfectly, doesn't it? Because if you are in this Lancer circle, then you definitely are someone that goes to Emmanuel. But it's not real satisfying to me, because what would something out here be, an X out here? You go to Emmanuel and you're not a Lancer? So we got a problem with this converse statement. It's not necessarily true. And you're going to see the same problem with the inverse. You got that stated? Inverse, we negate. Got it? If you do not go to Emmanuel, then you are not a Lancer. And let's see what the Euler diagram looks like. We're going to start with the one we just had with the converse. If you do not go to Emmanuel, the only place you can mark this one is way out here. So this statement would be true, that if you do not go to Emmanuel, then you are not a Lancer. It's not possible. But again, this statement doesn't quite make sense. But you should note this, that the same Euler diagram works for the converse and the inverse. I can show you that here. So there's from the converse. If you are a Lancer, then you go to Emmanuel. Has to be. And the inverse of that original, if you do not go to Emmanuel, well, that's got to be way out here, then there's no way you can be a Lancer. So these two statements are logically equivalent. They mean the same thing, even though they're not true. We can use the same Euler diagram for them. So notice which statements are logically equivalent. I've used that word a couple of times by noting which diagrams are the same. And since I've used it, I should probably tell you what it means. Means the same thing. That's the basic definition of logically equivalent. So we got a lot going on here, but you'll notice that, let me back up one, a little confusing. So here we've got these two use the same diagram. Go to Emmanuel is the hypothesis, conclusion there. And if you go to Emmanuel, then you are a Lancer. And if you are not a Lancer, then you do not go to Emmanuel. Here's the inverse and converse. If you are a Lancer, then you go to Emmanuel. Where's that one? Right here. If you are a Lancer, then you go to Emmanuel. And if you are not a Lancer, I'm sorry, if you do not go to Emmanuel, then you are not a Lancer. So these two diagrams work, and these two diagrams work together, so we say they're logically equivalent. So the original statement and its contrapositive, always logically equivalent. They mean the same thing. And the converse of an original and the inverse are logically equivalent. They mean the same thing. So let's try this out. We kind of talked about this earlier, but are all four conditional statements logically equivalent? Take a look at them. Maybe you remember them. It's not true right here, is it? If a polygon is not a rectangle, then it does not have four sides? No. Not logically equivalent. Neither is the converse. If a polygon has four sides, then it's a rectangle? No, no. But if a polygon does not have four sides, then it is not a rectangle. So the contrapositive contrapositive, and the original are logically equivalent, and the converse and the inverse are logically equivalent. So a quick review: conditional statement, remind yourself what it is. That'd be a good quiz question, wouldn't it? It has a hypothesis and a conclusion, an if and a then. And then there are some other types of conditional statements. Besides the original conditional statement, there's the contrapositive, the inverse, and the converse. And then remember the logical equivalents. Which ones mean the same? The original and its contrapositive, so these two, I guess, and then the inverse and the converse. What is a statement that can be represented symbolically by if A, then B? So recall what we talked about in class, or check out in the book. Now he's just trying to get you to name the parts of that statement. And then draw and describe an Euler diagram. If A, then B. So don't miss. Draw and describe. Next, we're working with this idea here. Sometimes the conclusion can be stated before the hypothesis. This happens a lot, so we don't want you to overgeneralize and always think that the hypothesis comes first. Look at the two statements. They both have the same hypothesis. What is it? Of course, with hypothesis, you're looking for the phrase beginning with if. So I see it here, and I see it there. So that's the hypothesis. But notice here, it's at the end of the sentence, and here it's at the beginning. That's the point. Same thing, check the conclusion. What is it? And are both those statements true? Think carefully about them. Two more statements. Do they have the same hypothesis? Again, what word are you looking for? Check it out. Are both statements true? Explain this one now for a second point. Why or why not? And do they mean the same thing? Think about it a little. I think you'll get it. Rewrite the first statement so that the conclusion is stated before the hypothesis. They are not saying interchange them. They're just saying rewrite it. The hypothesis is still the hypothesis. Conclusion is still the conclusion. We just want the conclusion first. And is that statement true? All right, he goes on. It is possible to compare the following three statements, even though you probably don't know what they mean, like what is a quoit or a bob, ring the same bob, and so on. So let's try to compare these. Which two statements have the same hypothesis and same conclusion? What are you looking for hypothesis? You're looking for the word if. Conclusion, the idea of then. Notice I said idea. Sometimes you'll see the word then, sometimes you'll just hear the idea of then. Do the two statements that you found in number 12, do they mean the same thing? This next section is a practice in writing conditional statements, writing them in if-then form. And he has a little fun with the statements here, as you'll see. He gives you an example, though. He says, be careful not to change the meanings of the sentences. For example, if you write a true statement in if-then form so that it turns out to be false, something is wrong. Here's an example. Genuine phone numbers do not begin with 555. We're starting with that. Possible answers. If it is genuine, it does not begin with 555. Genuine numbers do not begin. So if it is genuine, it does not begin with 555. Here's another one. If a phone number begins with 555, it is not genuine. Oh, that's interesting. What did they do? Did you pick up on that? Anybody recognize the contrapositive? they interchanged. They put this conclusion first and they negated it. Instead of not begin with 555, they said it begins with 555. Then they took the hypothesis and made it the conclusion, but negated it. It started out as, if a phone number is genuine, they said it is not genuine. So the contrapositive is true. These two are true. What you couldn't say here was something like this. If a phone number is genuine, then it begins with 555. That's what he's trying to get across. So here are your examples. You're writing them in if-then form. Make sure they always say the same thing. Getting into some Euler diagrams now. Write a conditional statement. So remember an Euler diagram. If A, then B. Little circle, big circle. So write the conditional statement represented by the Euler diagram below in the form if A, then B, and make sure you get the right A and B. Rewrite it in the form B if A. Not interchanging the hypothesis and conclusion, just writing the hypothesis at the end, the conclusion at the beginning. The author thinks that at this point you should keep in mind that with every Euler diagram, you might think there are only two spots in the A circle, in the B circle, but there's also a third location, a third region, and that's outside of both of them. This would come into play as we had in class where we said not B. So if not B, then it's also not A. Couldn't be. So there's three regions here, and he has 4 questions about those regions. Next, you're going to draw some Euler diagrams. Guess I've kind of given you them here. Try that second one on your own. This one. Try that before you see mine. If y, then x. Not a hard thing. There it is. Now, which of these diagrams, first one or the second one, also illustrates the statement, if not x, then not y? So you ask yourself, does this diagram show that if it's not in x, then it's not in y? Nope. Here's a spot right here that's not x, and it's not y, but it is y. How about this one? If it's not x, then it's not y. Well, that makes sense because the only place not x can be is in this third region out here. And that's certainly not y. Same logic on 29. Figure that one out. Hope you're pausing in between here. I'm moving right along from one to the next. How many if-then statements does a given Euler diagram represent? Think about that. We've got all 4 of them here. Then you need to figure out from your answers how many apply to each Euler diagram. Again, drawing another Euler diagram to represent that statement. All players for the Yankees make a lot of money. Are you picturing that one? Think about that a minute. See if you can get that before you see mine. All players for the Yankees make a lot of money. What's the if part? That's how I ended up with it. If you're a Yankee, then you make a lot of money. So you're going to use that Euler diagram to answer these questions. Which ones are illustrated by this Euler diagram? We just learned that all Euler diagrams can represent 2 of the conditional statements. So look that through. Good practice would be to name each one of these. If this is the original, what's this one, that one, and that one? Which of those statements are true that you wrote up above, A, B, C, and D? Which ones are true? Another example here, an octogenarian. I think that's an 80-year-old. So make an Euler diagram. If you have lived a long time, then you are an octogenarian. I guess I jumped the gun here. If long time, then octogenarian. Again, which 4 are illustrated by the diagram? You could try to name those again for practice. And which do you think might be true? Set 3 is an interesting experiment with some monkeys, or chimps, I guess, to show that particular one, Sarah, could interpret sentences using conditional statements. So here we have a conditional statement, and this green triangle is the one that Sarah recognized to know that it was if-then. Green triangle with the 3 holes. So this conditional statement is this: if Sarah takes the apple, then Mary will give chocolate to Sarah. Before you move on, try to figure out what each of these symbols are. That will make it easier as you go on. So pause and think about that. If Sarah takes apple, then Mary will give chocolate to Sarah. I think that'll help. So which shape do you think is Sarah? Where does the hypothesis appear in the arrangement of the shapes? Here's a second statement. Now, they don't give us quite as much. They just tell us that banana is in it somewhere. What shape do you think represents the word banana? What do you suppose this statement says? All right. Work this through and bring any questions you have to class.